Hello, everyone. Hope you guys see my screen and hear me properly. Can you guys hear me? Hello.
Yes, we can hear you.
Okay, thanks. Just want to verify. All right, so hi, everyone. So my name is Lochana Palayangoda. I'm an assistant professor of data science and statistics at University of Nebraska, Omaha. Today my presentation is about my recent research on distribution-free statistical approaches to estimate the lifetime of products which are subject to degradation, and using a specific experimental setup called step stress degradation. So I'll go into detail about it and introduce what is that in a second. As you know, by the emerging technologies in the market, you can have a lot of high-tech products which have very long life. One of the ways to estimate those long life products are using, or highly reliable products are using, depreciation data or degradation data. So as you can see in this slide, you can see LED. When you have LED lamp at the first day, and it can, after 3 years, you have light depreciation over the time. And that depreciation data can use as a source to estimate the lifetime. And the manufacturers claims that if you have 70% of the initial light output for LED, it can categorize as a failure. So what we are doing in experiment is that we do the experiment for maybe like 6 months or so, and then because of the time and money that we have, and we extrapolate the lifetime that is reached to a predefined threshold level of depreciation or degradation of the product. And the variable that we have here, which is TC, which is a failure time, it is a variable. This is more like a random variable, which is not constant for a product to product. So we can find a probability distribution for that. So to find that probability distribution is called the jargon is the first passage time distribution, or you can also call it as a popular name as failure time distribution. And so we can easily estimate that using straightforward applications like probability models that we can have. So one of the ways that I'm trying to explain is that so we have this degradation data, and so let's assume this like a intermediate or consecutive time measurement differences between degradation is delta X. We use a specific model, a stochastic model, more like a time-dependent models to estimate this failure time data, which is called a specific stochastic process called Levy process. In here, we assume these differences are independent for each other, and they follow the same probability distribution. So with that strong assumption, there are a lot of models have been developed using different Levy process-based models, which are called Wiener process. I hope you know the Gaussian distribution or normal distribution. Using the normal distribution or Gaussian distribution, we can create the process called Wiener process if your degradation data follows normal distribution. There are other distributions like gamma and inverse Gaussian distributions. You can directly find these failure time distributions, but these models specifically use a predefined distribution like normal distribution, gamma distribution. So one of the problems with these predefined distribution is that you can always have a misspecification errors. So for these misspecification errors, we'll create like errors when for example, if manufacturer comes up with this, failure time data and distributions, and if they come up with the warranty information for their products, it can impact some kind of a misspecified error if you come up with these predefined predefined distributions. So about 2 years back, we proposed a specific model which we can use the model find the failure time distributions of these reliable products without using any predefined distributions like normal distribution, gamma distributions. It's purely a data-driven. We are not using any distributional assumption, prob distribution assumption to find these failure times. So we use a model, a specific approach called saddle point approximation method. And we show that this model is very, using this approach is very robust, it's data driven, and we can get rid of these model misspecification errors. So for example, if a person assumes the data follows a gamma distribution, but actually it's a Wiener or rather normal Gaussian distribution, so you can create that error. So in this approach, we could get rid of those errors from those approaches, but I'm not going to go through all this math, but if you have any questions, I can go through all of these details in later. But there's a specific experimental setup they have developed recently, which called the step stress degradation test. What it really does is we apply the stresses or temperature increases or pressure increases for the product systematically throughout the experiment time. For example, here we increase the temperature from 150 for some time and increase the temperature for 165 and 180 likewise. So what it really does is we can accelerate the depreciation or degradation of the product, so we don't need to worry about slow depreciation of the product. So we apply high stress systematically to accelerate our product depreciation or degradation. So for these kind of experiments have been very popular in the literature. There are a lot of studies have been done. One of the problems in these current studies are they use a predefined distribution, like they use normal distribution like Wiener process or gamma distribution like gamma process. So what we are proposing in this case is that to overcome that, because of these misspecification errors I mentioned again and again, so it will apply for these models in the literature as well. So in this study, we basically proposing distribution-free method for this step stress experimental setup, and I did some Monte Carlo simulations to validate our models, and then we apply in the operational amplifier data set. So if I briefly explain what a model is, it's basically, as you can see, these degradation data we model with mainly two items in this degradation. One is the average, other one is a variance of the degradation. So as you know, when the variance and the mean, or the average and the variance is changing with the stress level. So if you have higher stress level and higher stress level, the mean and the variance changes with that stress levels as well. So we want to come up with a model that will change the average and the variance change with the stress level that we apply, and then we can find out what's going to happen for this product in the ambient environment of 25 degree Celsius or 70 degree Fahrenheit environment. So first, what we did was we come up with a model to model the averages of the degradation, how it's changed with the temperatures or pressure. What we are doing in this step is we try to figure out what's the average degradation changes with the temperature or the pressure or any stress level that we apply. And then we can find some parameter estimates using that. So this is the mathematical equation related to that. And next, what we did was we tried to figure out how the variance changes with the when we change the variance of the data with the stress level, how we can model that. So we use a specific model type called exponential degradation models, so which we could figure out a way to find the variance changes of a degradation when you change the stress level. So once we come up with that mean changes or average changes with stress levels and the variance changes with stress levels, so we can transform our degradations into ambient temperature levels. All the degradation that we have, we transform the prevailing methods that we have, we could transform all of data into ambient environment. And then we have the degradation data for a given stress level of ambient data. And then we can find what is the failure time when the product operates in the ambient temperature or ambient pressure. So it will help us to get this one done without any distribution assumption. This is purely data-driven approaches we have done. And we did lot of simulations, but this is one of the section of the simulations I want to show you. So in these numbers in this table inside that you can see are errors, or it's also called mean square errors. So these errors, high errors means it doesn't work properly, low errors means it's work well. So as you can see, our blue one is a true distribution that we have defined. So we assume we generate the data from specific data type gamma distribution, and then we check with other kind of distribution what's going to happen to the failure time. So as you can see in all the cases of the distribution, these are percentiles, which is like first percentile, 50th percentile. So Wiener process, inverse Gaussian process did not perform well, which is like a misspecification errors we can easily see when you model the gamma data with Wiener, gamma data with inverse Gaussian, but if you used our method, which is in green color, it has lowest errors compared to other two methods. So, but we did like several other simulations. If you are interested, I can show you them later. And then what we did was we applied this into operation amplifier dataset. So what in that experiment, what they have done was they have the operation amplifiers. They use 150 as experiments starting in temperature and increase into 195 systematically as a step stress degradation data. But we have to test this failure time for 25 degrees, which is not we have tested. That's why we are using these models. We test this in the high stress levels to accelerate the degradation and then transform it back to the ambient temperature. And we found that our models are a little bit robust, what we have found. So if I explain to this chart in a little bit, so here we have the green color is with the normal assumption, or like a Wiener, it's called the Wiener process. The blue one is with the gamma distribution. The red one is the one that we are proposed model. And this one, this one is the light blue color one is the inverse Gaussian model. So what we have found was that in order to figure out the failure time data of a product, so our model is more data driven. It's not too extreme distribution. It's more like whatever the data that we are getting, it will give you better results compared to the parametric models, which is we believe more adaptive technique. So in summary, what we have done was we proposed a specific distribution-free method to find the failure time distribution. We use simulation, and we found that our proposed method is more robust and it's more data adaptive using our application that we apply. And so currently we submit this paper into a journal, and we are waiting for their response. I'm more than happy to answer any question that you have. Thank you.